Hello, this is Dr. Hanaa Assil, and this is a final review for paper 1C. So this is a very quick summary of everything you need to know for paper 1C. You know that there are some topics that are not included in this paper. So let us see the topics that are included. So the first thing is you should be familiar with these simple basics: separation of particles in a solid, a liquid, a gas. Of course, in the solid, we say it's close packed. Remember, is he asking about separation or arrangement or movement? So if he's asking about separation, solids are closely packed, liquids are near each other, gases are very far apart. But if he's asking about arrangement of particles, then you should know that solid is arranged in regular rows. Liquid and gas we refer to as random arrangement or irregular arrangement. Movement of particles in a solid: the solid particles vibrate in fixed position. Liquid particles move around each other, and the gas particles move in fast, free, random motion. Then the change of state, please don't make any mistakes in this. Solids changing to liquid, that's melting. Liquid changing to gas, that's boiling, or we could refer to it as evaporation. Now, when gas is cooled and gives a liquid, that is condensation. When liquid is cooled and becomes a solid, that is freezing. And we said that some solids, when you heat it, it becomes gas directly, and that is sublimation. Then you should be familiar with the fact that if something is a solid at a certain temperature, that means that we have not yet reached its melting point or its boiling point. That means it has high melting point, high boiling point. Either it is if he's talking about room temperature or if he's talking about any other temperature, then the melting point and boiling point will be higher than that temperature. Now, liquid, if something is a liquid at a certain temperature, that means we have passed its melting point. So its melting point is low, but we have not reached its boiling point yet, so the boiling point is high. If something is a gas at a certain temperature, that means we have passed its melting point, we have passed its boiling point, and that means it has low melting point and boiling point. Then you should be familiar with what is diffusion. We said if we put a particle of potassium permanganate, for example, at the bottom of the beaker, slowly the purple color will spread. Why is it spreading? Because molecules are moving from area of high concentration to area of low concentration down the concentration gradient by the process of diffusion. Definitions: what's an element? Element contains only one type of atom. Don't say one atom. It has many, many atoms, but all of them are the same, identical, or the same type, then it's an element. A compound is made up of two or more elements chemically combined together in a fixed ratio. If you still don't know these definitions, please make sure you memorize them. Mixture is made up of two or more substances added together and can be separated easily, or it can be separated by simple physical processes. Solutions, of course, are examples of mixtures. Now, the solute is the substance that is dissolved in the solvent, and the solvent is the substance in which a solute is dissolved. So here, for example, the sugar would be solute, the water is the solvent. Then we say, what is a pure substance? It's something that does not contain impurities. Now, if something is pure, how can I tell that it is pure? It will have a fixed, sharp melting point if it's a solid, or a fixed, sharp boiling point if it's a liquid. Now, the presence of impurities will cause it to melt at a lower melting point than it should be. So anything that has a solid that has impurities will have lower melting point. A liquid that has impurities will boil at higher boiling. Then how do we separate mixtures? We said if I have something that is insoluble and I want to separate it, of course we separate it by filtration through filter, paper, and funnel. If we have a solution and I want the salt, then we do crystallization. And please pay attention to the description of crystallization. Some students miss the points. When we do crystallization, the first thing we do is heat to point of crystallization. Then we cool. Then we filter. Then we dry the crystals. Okay? So heat to point of crystallization, cool to allow it to form crystals, then filter through filter paper and funnel to obtain the crystals. And then if you want it dry, you should dry the crystals between filter papers. So how do I know that I have reached the point of crystallization? We say insert a glass rod and remove it. Crystals should form on the tip. And you should realize that when I heat a solution to point of crystallization, I am actually making a saturated solution. So I am heating it to point of crystallization. That means I'm removing as much water from it as possible. So I'm left with a solution in which no more solid can dissolve at that temperature. So if he says what is meant by a saturated solution, it is one in which no more solid can dissolve at a certain temperature. We use simple distillation if I'm trying to get water from a solution. So I have a solution and I'm trying to get the water. Of course, if we say what is the function of the condenser here, the condenser is to cool and condense the vapor. We use fractional distillation if I'm trying to separate a mixture of liquids. And the property we're depending on here is boiling point. So they have to be a mixture of liquids with different boiling points. Then I use fractional distillation, which has a fractionating column. And we collect first the liquid with the lower boiling point. So when we heat it and we reach the lower boiling point, the first liquid with the lower boiling point comes out. During that time, the thermometer remains constant. The temperature does not change until all of that first liquid has been collected, and then the temperature starts to rise. Please note that in both simple and fractional distillation, the water going into the condenser has to go in from down and go out from the top of the condenser. And if he says why it is going in this way, we say to fill the condenser with water for more efficient cooling. Okay, then paper chromatography. You should know that paper chromatography is used to determine how many spots in a dye or in ink, how many colors, how many constituents. So you should be able to explain how to do chromatography. We say put a spot of the sample on the baseline near the bottom of a chromatography paper. Then put the paper into a beaker containing a small amount of something. Of what? If we're talking about dyes or ink or food coloring, then my solvent should be water. So don't just say solvent. We put it into a beaker containing a small amount of water. If we're working with anything else, or he says that it is something that is insoluble in water, then we say put it in ethanol. So we put the paper into a beaker containing a small amount of water, allow the water to move up the paper, and determine how many spots are obtained. Now, you should realize that we draw the baseline in pencil. Why is that? Because it doesn't dissolve in the solvent. We have to have the level of the solvent below the baseline. Why is that? So that the spots do not dissolve in the solvent. Then if we're trying to determine the presence of something, we can put the spots of different substances next to each other and determine which one goes up the same height. So if the spots go up the same height, they're the same. So for example, this one, A and 1 are the same. Now, another way of identifying something would be to use RF value, and you have to remember RF value of something. So let us say we're trying to get the RF value of that red spot. It is the distance traveled by the spot. so the distance from the baseline to that spot, over the distance traveled by the solvent, so the distance from the baseline to the solvent. So RF value is distance from baseline to spot over baseline to solvent front. Solvent front is where the solvent went up in the chromatography paper. So that is the RF value. Remember, if we're doing chromatography of something like sugars or amino acids, these are things that are not colored. So I will not see any spots on the chromatography paper. In that case, you should tell him that we should spray the chromatography paper with a locating agent in order to give the spots color and make it visible. Okay, I hope you remember all of these things. Now, we talked about atomic structure and we said the nucleus in the middle contains protons and neutrons with electrons revolving around the nucleus. And we said the neutron has a mass of 1. And that is the same as the mass of the proton. So both proton and neutron have a mass of 1, but the electron has a very, very small mass, which is 1 over 18/4. For charge, we say the neutron has no charge. Proton, the charge is +1. Electron, the charge is -1. Remember that the things inside the nucleus are called nucleons. So if we're saying nucleon, nucleon is the proton and neutron in the nucleus. Then we know that we have 2 numbers in the periodic table for each element. We have a smaller number, which is the atomic number, and that is the number of protons. And we have a larger number, which we call the mass number or the nucleon number, and that is the total number of protons and neutrons. So if I want to know the number of protons, it is the small number. So aluminium, for example, has 13 protons. It is also the same as the number of electrons if the atom did not gain or lose any electrons. So aluminium as an atom would also have 13 electrons. Now, what is the number of neutrons? It is the big number minus the small number. How are the electrons distributed around the atom? The first energy level takes 2, the second energy level can take up to 8, and then the rest goes into the next energy level and so on. So this is called the electron configuration. What is meant by isotopes? You should remember that if I have different types of hydrogen atoms, for example, these are called isotopes. So isotopes are atoms of the same element. They all have to be the same element, having the same what? Number of protons. So they all have the same number of protons, but different number of neutrons. And remember, if he says isotopes have the same chemical properties, this is because they have the same electron configuration. They have the same total number of electrons, 283, for example. The relative atomic mass is the average of the mass number of the different isotopes in the ratio of their occurrence in nature. Remember, all mass numbers that you have in the periodic table are relative to the mass of an atom of carbon-12. So if he gives you the abundance of 2 isotopes, for example, of chlorine, how do I get the relative atomic mass? It is the mass number of the first one times its abundance, plus the mass number of the other one times its abundance divided by 100. So here the relative atomic mass of chlorine is 35.5. In the periodic table, we know that we have vertical columns called groups and horizontal rows called periods. And you should remember that the number of the group indicates what? Indicates the number of electrons in outer shell. So anything in group 1 has 1 electron in its outermost shell. Anything in group 2 has 2 electrons in its outermost shell, and so on. So the number of the group is the same as number of electrons in outer shell. Now the number of the period indicates the number of shells or the number of energy levels. So lithium is in period 2. If you distribute its electrons, you'll find that it has 2 energy levels. Sodium is in period 3, has 3 energy levels, and so on. And you should realize that all elements in the same group have similar chemical properties because they all have what? They all have the same number of electrons in outer shell. They're in the same group. They don't have the same number of total electrons. They have the same number of electrons in outer shell. Group 1. Group 1 are called alkali metals. You should realize that these are the most reactive metals. They're also referred to as soft metals. And which one is more reactive? You should remember the one down is more reactive. Now, why is it that the one down is more reactive? For example, here cesium would be the most reactive. Why? Because as we go down, the atom becomes larger. So there is less attraction force between the outermost electron and the nucleus. So the electron outside is more easily removed. Remember that a metal is reactive if it loses its electrons easily. So as the atom gets bigger, that outer electron can be lost more easily. Remember that in group 1, as we go down, the reactivity increases, the density increases. But what happens to the melting point? The one up is the one that has higher melting point. Transition metals. If I say physical properties of transition metals, well, compared to the other metals, they are harder, higher density, higher melting point, and boiling point. But if he says characteristics of transition metals that do not apply to the other metals, then we say that transition metals form colored compounds, may act as catalysts, may have more than one valency or oxidation number. Group 7. Group 7 are called halogens. They are very reactive non-metals. The reactivity increases going up the group. So fluorine is the most reactive non-metal. Now, why is it the most reactive non-metal? It is the smallest atom. So it has very strong attraction forces between the outer electron and the positive nucleus. So it can attract the electron to it easier. Remember that a non-metal is more reactive if it can gain electrons more easily. Then you're required to know the appearance and the state of each of the halogens. So you should know that fluorine is a yellow gas, chlorine is a green gas, bromine is a reddish brown liquid, iodine is a gray solid. So as we go down, the color gets darker. So if we look at astatine, it would be a black solid. Now you should be able to remember that the one up in group 7 is more reactive than the one down. That means that it is likely to displace it. So if I react chlorine with potassium bromide, you should know that chlorine is more reactive than bromine. So it can displace it and I end up with bromine in my solution. So my solution turns orange. Or if I pass chlorine gas through potassium iodide, remember that chlorine is more reactive than iodine, so it will displace it, and I will have iodine in my solution, which forms a reddish brown solution. But if I'm starting with something that is less reactive, like iodine, it will not displace a more reactive metal from its solution. Remember also, a halogen cannot displace itself. I cannot say chlorine plus potassium chloride or chlorine plus potassium or iodine plus potassium iodide or something. Okay. Group 0 are noble gases. They have full outer shells. They are unreactive because they have full outer shells. And these are some of the uses of noble gases. Bonds, chemical bonding. Remember, if I have a metal and a non-metal, then the bond I have is ionic. And that means the metal, which has 1 or 2 or 3 electrons in its outermost shell, will lose this electron to form positive ions, and the non-metal will gain electrons to form negative ions. Remember, an atom is complete if it has a total of 8 electrons in its outer shell. So ionic bond, if he says what is meant by ionic bond, please do not say it's a bond between metal and non-metal. No, ionic bond is the strong electrostatic attraction forces. The word electrostatic may or may not be mentioned. So it is the strong attraction forces between positive and negative ions. So once I form Na plus and Cl minus, the attraction between the positive and negative ions, this is what we call the ionic bond. So you should practice drawing all of this. And sometimes he draws this for you and tells you what happens when lithium reacts with fluorine. Okay, you should realize lithium has 1 electron in its outermost shell. It needs to lose it. So we say that lithium loses 1 electron from its outermost shell and becomes lithium plus. If he's talking about the electron configuration, it changes from 2, 1 to an electron configuration of 2. Now, fluorine has 7 electrons in its outermost shell. It needs 1. So the fluorine gains 1 electron and becomes F minus with electron configuration 2, 8. The same for the others. Please practice all of this. Magnesium will lose 2 electrons. The oxygen will gain 2 electrons. Don't forget to write that when the magnesium loses 2 electrons, it becomes plus 2 or 2 plus. And when the oxygen gains 2 electrons, it becomes 2 minus or minus 2. The same for magnesium chloride, but here the magnesium needs to lose 2. Now each chlorine can gain only 1, so each chlorine gains 1 electron and becomes 1 negative. So I need 2 of them to take the 2 electrons from the magnesium. Sodium oxide, the oxygen needs to gain 2 electrons. Each sodium atom will lose 1 electron, become Na plus. So I need 2 of them to give 2 electrons to the oxygen, which will become 2 negative. You should realize what is the structure of an ionic compound. It is called ionic crystal lattice. This is a giant 3-dimensional structure with regular arrangement of alternating positive and negative ions. So in this case, each positive ion is surrounded by 6 negatives and each negative ion is surrounded by 6 positives. If he says how is this structure held, it is held by strong attraction forces between positive and negative ions. Why is it that ionic compounds have high melting point? You should realize this is because of the strong electrostatic attraction forces between what? Positive and negative ions. If he says mention bonding and structure, then you have to say in the giant crystal lattice, which need a lot of energy to be broken. Now, remember that something that has more charge would have higher melting point. So Mg2 plus O2 minus has more charge than Na plus Cl minus, so that would have higher melting point. Remember, ionic compounds dissolve in water but do not dissolve in solvents like ethanol. Ionic compounds conduct electricity when what? Molten or in solution. So when molten or in solution, ionic compounds conduct electricity because the positive and negative ions are free to move. But they will not conduct electricity when solid because the ions are not free to move. Covalent bonds is between 2 nonmetals. So if I have 2 nonmetals, I have covalent bond. But if he tells me what is meant by covalent bond, it is the strong attraction forces between the bonding pair of electrons, so the 2 electrons that are being shared, and the positive nuclei of the atoms. Remember, we have 2 atoms sharing the electrons. So these shared electrons are being attracted to both nuclei of both atoms. So you use the plural nuclei, not nucleus. Again, please practice drawing this. Hydrogen has 1 electron in the first shell. It needs only 1. So this is the dot and cross for hydrogen. You can draw it with circles or without circles. Chlorine molecule means I have only chlorine atoms and each atom needs 1 electron. So they're going to share 1 pair of electrons. Water is between oxygen and hydrogen. Remember, oxygen has 6 electrons. It needs 2 more. Each hydrogen can donate 1. Please do not forget that the oxygen still has the rest of its 6. So don't forget those 4 electrons outside around the oxygen that are not involved in bonding. Then we say methane. Methane is carbon. Carbon is in group 4. It needs 4 more electrons. So each hydrogen can donate 1. So that's why the carbon has 4 hydrogens around it. Ammonia, please pay attention. Nitrogen is in group 5. It has 5 electrons in its outermost shell. It needs 3. So it will need 3 hydrogens to donate 3 or to share 3 electrons. It still has 2 more around it. Please don't forget the 2 electrons remaining on the nitrogen that are not involved in bond. Hydrogen chloride, please sit down and practice drawing all of this. Carbon dioxide is very important. Ethene, methanol. Methanol has 3 different atoms, so you need 3 different notations. So you can use an X with a circle or a dot with a circle or a small circle or an open circle or whatever. Okay, but don't forget the extra electrons on the oxygen. Oxygen has 6 electrons. It's going to use 1 to share with carbon, 1 to share with hydrogen, and it still has the rest of its 6 around. Okay, you should know covalent compounds have low melting point and boiling point. Why? Weak attraction forces between molecules that need a small amount of energy to be broken. Covalent compounds are insoluble in water. They will dissolve in things like ethanol. Covalent compounds do not conduct electricity at all. So if he gives a table and he gives something that does not conduct electricity, whether solid or liquid, then this is a covalent compound due to what? Due to the absence of free ions. They actually don't have free ions or free electrons. Then we have 2 types of structure. We have simple molecular structure. So things like iodine and carbon dioxide, we say they have simple molecular structure. Now, anything with a simple molecular structure would have low melting point. Now, why does it have low melting point? Because there is weak attraction forces between molecules that need a small amount of energy to be broken. So please, this explanation for low melting point goes to anything that has a low melting point. It will be due to weak attraction forces between molecules that need a small amount of energy to be broken. Now, anything that is not a simple molecular structure would be a giant macromolecular structure. So the word macromolecular means giant structure. That is large 3-dimensional structure in which many atoms are strongly bonded together. Now, an example of that is diamond and graphite. And you should realize that diamond and graphite are both elements. They are both made of carbon, but they have different structures. Now, they are giant, so they have high melting point. Now, why do they have high melting point? Due to strong covalent bonds between the atoms. Don't say attraction forces. Strong covalent bonds between the atoms in the giant 3-dimensional structure, and this needs a lot of energy to be broken. So please, diamond and graphite have high melting point, not because of strong attraction forces between something. It is because they have strong covalent bonds between atoms in a giant 3-dimensional structure, and this needs a lot of energy to be broken. Ionic crystals. Any ionic compound is also giant. It is giant 3-dimensional structure with regular arrangement of alternating positive and negative ions. Now here, if I say, why does it have high melting point? How will they have high melting point? Because of the strong attraction forces between positive and negative ions or oppositely charged ions. If he says describe the structure of diamond, it's a giant 3-dimensional structure in which each carbon atom is what? Covalently bonded to 4 other carbons, and this kind of structure is called tetrahedral structure. So this, because of its structure, diamond is hard. So diamond is hard because of the strong covalent bonds between carbon atoms in the rigid 3-dimensional tetrahedral structure. Now diamond does not conduct electricity because of the absence of free electrons. Remember, we don't mention ions unless if we're talking about ionic compound. Otherwise, we're talking about electrons. Now, diamond is used in cutting and drilling because it is hard, because it has strong covalent bonds between the carbon atoms in the rigid three-dimensional tetrahedral structure. Now, when we come to graphite, it still has strong covalent bonds between carbon atoms, so it has high melting point. But remember that it is soft. Now, why is it soft? Because of weak attraction forces between the layers that allows them to slide past each other. Remember that graphite is the only non-metal that conducts electricity, and that is because it has free electrons. Now, why does it have free electrons? Because each carbon is covalently bonded to only 3 other carbons. So it has a 4th electron for each carbon atom that is free to move between the layers. We use graphite for what? We use graphite as a lubricant because it is soft. Or we could be using it as an electrode because it conducts electricity. Now, there is a third form of carbon, which is fullerene, C60 fullerene. These are structures made up of 60 carbon atoms joined together in a structure of pentagons and hexagons. Now, remember that when I say the molecule is made up of 60 carbon atoms, this is actually a small molecule. So these are simple molecular structures, so they have low melting point. Now, why do they have low melting point? Simple molecular structure with weak attraction forces between molecules that need a small amount of energy to be broken. Then, how do we write chemical formula? Remember, to write the chemical formula of something, you write the symbols and then you put the valency of one under the other. How do we get valency? Well, there are things in the periodic table that we can get the valency from. So anything in group 1 has 1 electrons outer shell. It needs to lose it. So its valency is 1. Remember, the valency is number of electrons lost or gained in order to have a full outer shell. So group 1 needs to lose 1. Group 2 needs to lose 2. Group 3 needs to lose 3. Group 4 will share or take 4. Now, the ones in group 5 has 5 electrons in its outermost shell. It needs 3, so we say its valency is 3, 6, valency 2, 7, valency 1. And then the atomic groups are things that you have to memorize. So this list, hydroxide, nitrate, nitrite, ammonium, carbonate, sulfate, phosphate, you're supposed to have memorized them with their valencies because there is no way that you're going to be told about. Okay. Now, transition metals, what are the valency of transition metals? We said transition metals have different oxidation or more than one oxidation number. So we usually write their valency or their oxidation number between brackets. So if I say iron 2, that means I'm talking about the iron that has a valency of 2. So when I write the formula, I write the 2 under the other element, not under the iron. Remember, we write the valency of something under the other one. So I can have iron 2 or iron 3. So when we talk about iron, he has to tell you which iron he's talking about. But copper is usually 2, even if he doesn't tell you. Silver is usually 1, even if he doesn't tell you. Now, zinc is 2, and he will never tell you the valency of zinc. You are supposed to know that it is 2. How do we write the formula of acids? We start with H, and then depending on which acid we're talking about, the acid that has chloride or nitrate or sulfate or phosphate, these are the different acids that you will be required to write. When he says mono or di or trioxide, that means I give him 1 oxygen or 2 oxygens or 3 oxygens, and we forget about the valencies. We don't think about the valencies because these are exceptions. So if he says nitrogen monoxide, it's N with 1 O. Carbon monoxide, carbon with 1 O. Nitrogen dioxide, nitrogen with O2, and so on. And you forget about the valencies. Remember, when you write any chemical equation, you have to balance it, even if he doesn't tell you. We cannot have a chemical symbol equation without balance. Now, if he asks for state symbols, you should be able to say whether it's an S or a G or an L or an AQ, depending on what we're talking about. Also, you should know that some molecules are diatomic. So when the equation says plus hydrogen, plus nitrogen, plus oxygen, These are diatomic, so they cannot stand alone. They have to be, the molecule has to have two atoms. If we say, what do we mean by diatomic? It's a molecule made up of two atoms. So these are equations that you can practice balancing and writing them. Okay. Acids and bases. Acid is a proton donor. Base is a proton acceptor. Alkali is a base that dissolves in water. And salts are ionic compounds produced from the reaction of acids and base. You should realize that when I say that something is concentrated, it means it has a very small amount of water. If it is dilute, it has a lot of water. And then you should be familiar with these pH values for strong acid, weak acid, neutral, and so on, so that you can predict, he can say predict or suggest the pH of vinegar, for example. You should remember that vinegar is weak acid, so the pH you write should be 4 or 5 or 6, and so on. Definitions of strong acid, strong base, weak base. Remember, the strong one ionizes completely. The weak one ionizes partially. You should know that an indicator is a substance that has different colors in acids and bases. So we talk about litmus paper. You should realize that litmus paper has a red color in acids and a blue color in base. But if we want to determine the pH of a solution, we have to tell him, insert universal indicator paper and compare the color to the chart. And you should realize that if something is neutral, it will give green. If something is strong acid, it is red. Something that is a strong base, it is blue. And something that's a weak acid will either be orange or yellow. Colors of phenolphthalein, please be familiar with it. It is pink in base, neutral in colorless in neutral. Methyl orange is yellow in base and orange in neutral. Reactions of acids and bases, we said acid plus base to give salt plus water. That is called neutralization reaction. An acid would also react with a metal. In this case, it forms salt plus hydrogen, or it can react with a carbonate to give salt plus carbon dioxide plus water. You should know ammonia is a base, so it should react with acid, but it is the only base that does not have oxygen, so it will give only salt. Not like other bases. We said a base would give, acid plus base would give salt plus water, but ammonia will react with acid to give only the salt. So either I have ammonium chloride, ammonium nitrate, ammonium sulfate, and so on. It forms the ammonium salt. HCl. You should remember that HCl is unique. As a gas, we say it is hydrogen chloride gas and it is covalent. Now, when we dissolve it in water, it ionizes to form H plus ions, so I form an acid. So HCl becomes, in water, it becomes hydrochloric acid. But if we dissolve it in any other solvent that's not water, then it will not ionize, so no acid is formed, so it will not do the reactions that are for acids. Okay, what type of oxides do we have? We said oxides of non-metals are usually acidic, but there are exceptions. Some of them are neutral. So carbon monoxide, nitrogen monoxide, and of course H2O, which is the oxide of hydrogen, is neutral. Now, oxides of metals are basic. So oxide of a metal is basic, except the oxide of zinc, aluminium, and lead. These are amphoteric. Now, what's the importance of this? You should realize that any acid can react with only base. So acidic oxides react with base. Basic oxides react with acids. Now, amphoteric can react with both. So the amphoteric will react with both acid and base. Neutral do not react with acids, do not react with base. So why do we say it's basic? Magnesium oxide, for example, if I dissolve it in water, it forms magnesium hydroxide. That's a base. But if I have oxides of non-metals, when I dissolve them in water, they form acids. So you should remember, carbon dioxide dissolved in water forms carbonic acid. Sulfur dioxide dissolved in water forms sulfurous acid. Sulfur trioxide dissolved in water forms sulfuric acid. Then you should be familiar with what is soluble and what is insoluble, because he will ask you to write state symbols, and you should be able to tell, will this be a solid, forms precipitate, or it is aqueous, so it dissolves in water. So what are soluble? You should know anything nitrate is soluble. Any nitrate is soluble. Sodium compounds, potassium compounds, ammonium compounds, they're all soluble. So sodium, potassium, ammonium salts are all soluble. All acids, their state symbol will be aqueous. Now, things that we work with like barium chloride, magnesium chloride, calcium chloride, copper sulfate, all of these you should know are soluble. Now, what is insoluble? Most carbonates are insoluble. So barium carbonate, calcium carbonate, and actually copper carbonate also. All of these will form precipitate, so their state symbol is S. Silver halide, lead halide, barium sulfate, copper oxide, and of course all metals, all of these are insoluble, so their state symbols would be S. Okay, when doing a titration, there are some things that we should realize. So first of all, usually the flask that I'm doing the titration in should be placed on a white tile or a white paper. And if he says why, it is to see the color change clearly. Then what should I be doing to the flask during the titration? Well, the flask should be swirled while adding the solution from the burette to mix the contents. And then when you read a burette, you should know that your eyes should be on the same level as the meniscus. Where is the meniscus? The meniscus is that bottom part of that bent surface of the liquid. So we read the bottom of the meniscus in order to get the volume. In titration experiments, he will tell you that I wash the burette twice. I wash the burette first with water and then with the solution that I'm supposed to fill it with. So why am I washing it with water? I tell him to remove traces of previous solution. So why are we washing it with the solution I'm going to fill it with in order to remove the water? Because if I fill it with a solution and that burette had water in it, it will change the concentration of my solution. So we wash with water to remove traces of previous solution, and we wash with the new solution to remove water. Tests. Please don't go to the exam without learning the tests. Very quickly. Test for carbonate, add dilute hydrochloric acid. My result would be bubbles of gas that turned lime water milky. If he asks for the name of the gas, then that is carbon dioxide gas. Test for halides. I add dilute nitric acid and aqueous silver nitrate. If it's a chloride, it gives white precipitate. Bromide, cream precipitate. Please learn the spelling of the word precipitate. Iodide will give a yellow precipitate. Test for sulfate. Add dilute nitric acid and barium nitrate. Or it could be dilute HCl and barium chloride. If I have a sulfate, I will get white precipitate. Now, why are we adding the acid in the first place? To remove any carbonate present that would form a white precipitate even if the sulfate is absent. Test for ammonium. Ammonium salts or aqueous ammonia. I add, you have to tell me first what am I going to add. Add aqueous sodium hydroxide and warm gently. What should I get? Bubbles of ammonia gas given off that turn damp red litmus paper to blue. Test for copper ions. Add aqueous sodium hydroxide. I get light blue precipitate, insoluble in excess. Test for iron 2 and iron 3. I add sodium hydroxide. If it's iron 2, it gives green precipitate. If it's iron 3, it gives reddish brown precipitate. What was test for ammonia gas? Insert damp red litmus paper, it turns to blue. Test for carbon dioxide gas. Pass through lime water, the lime water turns milky. Here, please pay attention. You need to know why the lime water turns milky. You should realize that lime water is actually calcium hydroxide. Now, when I pass carbon dioxide through it, it forms calcium carbonate, and that is insoluble, so it causes the white precipitate, or it causes the solution to become milky. Test for chlorine gas. Again, pay attention. Is he asking for chlorine gas or chloride? Chloride, we said add dilute nitric acid and silver nitrate. But for chlorine gas, we say insert damp blue litmus paper, it bleaches. Test for hydrogen gas, insert a lighted splint, it pops. Oxygen gas, insert a glowing splint, it relights. Flame tests. In order to do a flame test, I need to clean the platinum wire first by dipping it into concentrated HCl. If he says, why am I doing that? To remove traces of any previous ions which would affect the color. Then I dip the wire in the salt and then expose the wire to what? To the non-luminous flame of the Bunsen burner. Observe the emitted light, and you have to remember these colors. Lithium will give red, sodium yellow, potassium lilac, calcium brick red, copper blue green. Okay? Test for water. It can either be chemical test, add anhydrous copper sulfate, it turns from white to blue, or physical test, heat the liquid to boiling, it should boil at 100 degrees centigrade. Test for alkenes. We said for alkenes, I add what? I add bromine water. It turns from reddish brown to colorless, or you could say orange to color. And then you're supposed to know these colors and these states. These are the things that you need to know. Remember that we said halogens, fluorine, yellow gas, chlorine, green gas, bromine, reddish brown liquid, iodine, gray solid. The copper as a metal is reddish brown, but as a compound, it is mostly blue. Copper carbonate is green. Copper oxide is a black solid. Magnesium oxide is formed when you burn magnesium. This is a white ash. Nitrogen dioxide gas is formed if you heat a nitrate. So this is a reddish brown fume. Carbon is a black solid that you could get from incomplete combustion. And manganese dioxide is a black solid that we use as a catalyst for breaking down hydrogen peroxide. So very quickly, let us go over this. The chemical calculations, please revise it. You get questions about this in both papers. The easiest thing would be to calculate the molecular mass. Of course, the molecular mass is the mass times how many I have, and the mass is the big number, please. So magnesium, its mass is 24. I have 3 of them, plus I have phosphorus, which is 31, and I have 2 of them. Remember that what is outside the bracket applies to everything inside the bracket. So the 4 applies only to oxygen, but the 2 applies to the PO4, all of it. So that means I have 2 phosphorus and 8 oxygens. So that is the total of all of that. Again, barium nitrate is in the same way. I have 1 barium, 2 nitrogens, and 6 oxygens. Then you will be required to get the empirical formula and the molecular formula. So he gives you percentages. So this percent potassium, percent iodine, and he's saying the rest is oxygen. Of course, the rest will be the rest of the 100. So I add 18.2 plus 59.4 and subtract from 100. That gives me the oxygen. Now, how do we calculate empirical formula? We first divide by the mass number of each one. Again, the mass number is the big one. So potassium divide by 39 and so on. And I get these numbers. Now I look at these numbers and I divide by the smallest so that I can get the simplest ratio. And that gives me the empirical formula. So if I have an example like this, he gives me percent lead and percent oxygen. Again, the first thing I do is divide by the mass number. I get 2 numbers, then I divide by the smallest. Now, in this case, when I divided by the smallest, it gave me 1 to 1.3. Please do not round that up. If I have 1.3 or 1.4 or 1.5 or 1.6, I have to multiply by a number that changes it into a whole number. So you will find that if I have something 0.3, I will have to multiply through by 3. So instead of 1 to 1.3, it is 3 to 4. So please do not make it 1 to 1 or something like that. So this is PB3O4. This is another kind of question where he says I have X water and I'm trying to get how much is the X water. So we heat the hydrated salt and we use that to get the X. So he has the mass of the crystals before heating. So this is the mass of everything with water. And then the mass of crystals after heating, so that is the magnesium sulfate without the water. So of course, if you have the magnesium sulfate without the water, that's the 8.3 grams. Now, how do I get the mass of the water? It is the difference of the masses. So I can do this as if I'm doing empirical formula, and I can get what was X. Number of moles, mass over molecular mass. Number of moles, volume over 24 if we're talking about a gas. Number of moles is concentration times volume if we're talking about a solution. Remember that volume in all these cases has to be in decimeter cubed, and then we can use this for calculation. Remember that there is Avogadro's law, and Avogadro's law says 1 mole of any substance has 6.02 times 10 to the 23 molecules. So if he's saying I want to know the number of atoms or the number of molecules, you multiply the number of moles by 6.02 times 10 to the 23. How do we calculate percent purity? If he says I have a certain mass of an impure substance, I use the information he gives me to determine what is the actual mass that reacted, and I divide that by the mass of the impure times 100. That gives me the percent purity. If he wants percent yield, that means that he said he got a certain actual yield. I need to calculate the theoretical yield. How much should he have gotten? And I divide what he got by what he should get times 100. That gives you the percent yield. Limiting reactants or excess reactants, if he gives me information about both reactants. So here, for example, he's giving me information about nitrogen and hydrogen. I need to get the number of moles of each one. So number of moles of nitrogen, number of moles of hydrogen, compared from the equation. So looking at the equation, the number of moles of hydrogen should be 3 times that of nitrogen. So is the number of moles of hydrogen 3 times? No, it's much more than 3 times. So that means that the hydrogen is in excess. That means if I'm trying to get number of moles of ammonia, I use related to the nitrogen, not to the hydrogen. Hydrogen is excess. So we don't use it for any further calculation. We calculate everything based on the number of moles of nitrogen, and then I can get the mass of ammonia he's supposed to get. Are we following? If something is excess, then it is more than needed, so you don't use it in the calculation. Definitions: what is oxidation and what is reduction? If we're talking about oxygen, oxidation is gain of oxygen, reduction is loss of oxygen. If we're talking about electrons, oxidation is loss of electrons, reduction is gain of electrons. If we're talking about hydrogen, it is the same as electrons. Now, if the oxidation number increases, that is oxidation. If the oxidation number decreases, that is reduction. Please revise all of these things. You should know that the oxidizing agent is the one that was reduced. So if he says suggest an oxidizing agent for something, you can either use oxidizing agents like potassium permanganate. Potassium permanganate is originally purple, and you should know when it reacts, it becomes colored. Or we could use potassium dichromate. Potassium dichromate originally is orange. When it reacts, it changes to green. Now, a reducing agent is the one that was oxidized. So which reducing agents can we use? We can use carbon or carbon monoxide or metals because they tend to lose electrons. So if we say redox reactions. You should know that redox reactions are reactions that involve both oxidation and reduction. So if we have that first equation, now the copper oxide, we're going to say copper oxide lost oxygen, so that is reduction. The H2 gained oxygen, that is oxidation. Now, copper oxide was reduced, so it is the oxidizing agent. Hydrogen was oxidized, so it is the reducing agent. Now, this second equation, what happened to the Fe? It changed from oxidation number 0 to 2 plus, or it lost electrons, so that is oxidation. The copper 2 plus gained electrons or decrease in oxidation number, so that is reduction. Now, since the iron was oxidized, it is the reducing agent. Since the copper 2 plus was reduced, it is the oxidizing. What are reversible reactions? They are reactions that go both forward and backward without going to completion, and that kind of arrow in the middle represents reversible reactions. So if we have copper sulfate, remember the test for copper for water, if I have copper sulfate that has water in it, that is blue. So this is the hydrated copper sulfate. Now if I heat it, I remove the water, so it becomes white, and that is anhydrous copper sulfate. Of course, if I add water to that white solid, it will turn again to blue. What is an exothermic reaction? It's a reaction that gives out heat. Gives out heat to what? To the surrounding solution. So if I measure the temperature of the solution, the temperature rises and the reaction becomes hot. And you should realize that all combustion reactions are exothermic. Now, endothermic is a reaction that takes in heat. So it's going to take in heat from what? From the surrounding solution. So the temperature of the solution decreases, the reaction becomes colder. So things like changing from solid to liquid to gas, you need to give it heat. It needs to take in heat, so that these are endothermic reactions. Now, if he says draw a reaction profile, if we're talking about an exothermic reaction, he said the reactants give out heat. That means the products have less energy than the reactants, and the difference between the reactants and the products is the delta H. So we say that delta H for exothermic reactions is negative. Now, where is the activation energy? It's from the reactants to the top. We said activation energy is the minimum amount of energy needed to start a reaction. But if he says draw the energy level diagram, then you just show where is the reactants and where is the products, and the delta H is from reactants to products. Endothermic reaction, we said the reactants take in heat. That means the products will have more energy. And the difference in energy between reactants and products is the delta H. So in this case, it is positive. And again, the activation energy is the difference in energy between the reactants and the very top. And this would be the energy level diagram for the endothermic reaction. Now, to calculate delta H, we do the reactions in a polystyrene cup. And if he says, why are we using a polystyrene cup? It is because it is an insulator for less loss of heat to the environment. So, how do we calculate delta H? We have a solution, and we're going to measure the initial temperature and the final temperature. And then I can calculate Q. Q is the total energy change. So the total energy change is mc delta T. M, you should remember, is the mass of the solution. So if he says I used 100 centimeter cubed, that is the same as 100 grams. The solution has a density of 1, or we're assuming it has a density like the density of water, which is 1, and that means the volume is the same as the mass, and that means if I have a certain volume of solution, that is the mass. So that is M. C is constant, 4.18, or sometimes he gives it to you as 4.2, and the delta T is the temperature change. Then I need to get the enthalpy change. The enthalpy change, delta H, is Q over N. So the Q that comes out from that equation is in joules. Q comes out from mc delta T in joules. Delta H we usually need to do it in kilojoules. So first we need to divide by 1,000, and then I put it into this equation, Q over the number of moles. You have to remember that delta H must have a sign. Now, how do I know what is the sign? Well, if he says there is a temperature rise or the reaction became hotter, then this is an exothermic reaction. So the delta H is a negative value, minus something. But if he says that the temperature went down or the reaction became colder, then that means that the delta H is a positive number and you have to put plus something in there. So the plus or the minus must be included. What are the factors that affect the rate of reaction? Remember, increasing the temperature increases the rate of reaction. Why? Particles gain more kinetic energy, move faster, collide faster, and more of the molecules have energy higher than activation energy. When we draw the graph, the one for the faster reaction is the steeper one. So that's the one above. And the one below is for the slower reaction, or it is less steep. Pressure, increasing pressure of gases increases the rate of reaction. Why? Particles are closer to each other, so more collisions. Surface area. We know that powdered or smaller pieces will make the reaction faster. So why is it that when I crush or use smaller pieces, it increases the rate? Because the powdered or the smaller pieces have larger surface area, so more particles collide at the same time, or you can say more frequent collisions. Increasing the concentration increases the rate, again, because if you have higher concentration, you have more molecules and you have more collisions at the same time, or more frequent collisions. A catalyst increases the rate of reaction without being changed. So remember, it increases the rate of the reaction, but if I start with 1 gram, I should end with the same 1 gram. Now, why does it increase the rate? Because a catalyst provides an alternative pathway for the reaction that lowers the activation energy. So when we drew this energy profile, if I'm drawing it with a catalyst, then the top of that activation energy will be lower. It lowers the activation energy if there is a catalyst. How do we study the rate of the reaction? Either we measure the volume of the gas every minute using a gas syringe, or we put it on a balance and measure the loss in mass every minute. Remember, or we can just say if it forms a precipitate, then we measure the time taken for the X to disappear. Then we talk about organic compounds. We know that they are covalent compounds, all made of carbon, and they were originally obtained from plants and animals. Alkanes are hydrocarbons, so they have only carbon and hydrogen. And if you look at the formula of each one, the general formula is CnH2n plus 2. The number of hydrogens is always twice the carbon plus 2. So you should know the general formula of alkanes. You should also know that all alkanes have only single bonds, so we call them saturated. And that means that when we say what is the functional group of alkanes, it is C, single bond C. For alkenes, the general formula is CnH2n. The hydrogens are always twice the carbons. They all must have the C double bond C, so we call them unsaturated. And the functional group we say is the C double bond C. So these groups are called homologous series. So each homologous series is a group of organic compounds having the same general formula, the same functional group, the same chemical properties. What are hydrocarbons? Remember, hydrocarbons are organic compounds made up of carbon and hydrogen only. Do not forget the only. How do we name organic compounds? One carbon is meth, F, prop, bute, pent. And then depending on whether we're talking about something that has only single bonds, so it should end with "ane", or something that has a double bond, it should end with "ene", and so on. Types of formula, if he says displayed formula, that means you need to draw everything out, all the atoms and all the bonds. If we're talking about structural formulas, you can collect the hydrogens around each carbon. If he says he wants molecular formula, then you count total number of carbons, total number of hydrogens, total number of oxygens, and so on. What are isomers? Isomers are two or more compounds having the same molecular formula but different displayed formula. So if he says draw isomers of propanol, well, prop means 3 carbons, all means OH. So how do I draw the isomers of propanol? I put the OH once on one end and once in the middle. Don't put it once on one end and once on the other end. No, these are the same compound. Whether it's on the end on this side or this side, it is the same. So once on one end, once in the middle, these are isomers. Now, if I'm drawing isomers of butene, again, butene must have a double bond. So once on one end, once in the middle. The double bond should change its position. That's all. These are isomers of butene. Isomers of pentane. Now, pentane doesn't have a double bond or an OH, it just has single bonds. So pentane, for example, has 5 carbons. So either I put all the 5 carbons in a straight chain, or I put 4 of them and then one of the carbons in the middle. Again, not on one end, in the middle. Or I can put 3 in a chain with 2 in the middle. These are isomers of alkanes. Remember that alkanes with small number of carbons are gases, and then as they increase, they become liquids. Methane is the main constituent of natural gas. It is used as fuel. Reactions of alkanes or alkenes, both of them do combustion. If I have lots of oxygen, it gives carbon dioxide plus water. If I have incomplete combustion, that means there is lack of oxygen, then I get carbon monoxide plus water, and I can also get carbon alone, which is the black soot that sometimes comes out when something is burning. Remember that carbon monoxide is poisonous, so it reduces the capacity of blood to carry oxygen. Now, alkanes, when they react with halogens, we call that substitution reaction. Alkanes do substitution reactions. We have to give them UV light, and what happens is I remove one of the hydrogens and I put a chlorine, and that means the other product is HCl. Now, that means that I can remove any of the hydrogens. So any of the hydrogens will be replaced by bromine, and that means it actually gives a mixture of products. What is cracking? It is the breakdown of long chain hydrocarbons into shorter chains. What are the conditions for cracking? Aluminium oxide catalyst at 600 to 700 degrees Celsius. It will either give alkene plus alkane or alkene plus hydrogen. Now, alkenes do addition reactions. So addition means double bond opens up and I put something here and something here. So in this case, this is called 1,2-dibromoethane. To distinguish alkenes with anything else, we add bromine water. Alkenes will change it from reddish brown to colorless because it will react to give this product, while anything else like alkenes, there is no change. Polymers. Polymers are large molecules made by joining small molecules together. The small molecules are called monomers, and the process is called polymerization. Now, uses of polymers. What do we use polymers for? Remember that polymers is the chemical name for plastic. So what do we use it for? In making the things that we make from plastic. Plastic bags, plastic bottles, plastic ropes, whatever. What are the disadvantages of the use of polymers, or the problems of the use of polymers? First of all, they're non-biodegradable, so they accumulate in dump sites. Remember, non-biodegradable means they cannot be broken down by bacteria. So we say they accumulate in dump sites. Now, the other problem is when burnt, they release toxic gases. Okay, how do we draw addition polymers? Remember the polymers, when we start with an alkene, this type of polymerization is addition polymerization. How do we draw it? We open the double bond, make it into a single bond, and bond on one end and one bond on the other. And then whatever each carbon was bonded to, I bond it again. So here it had hydrogen, so I bonded to hydrogens. Now remember, the name of the polymer is always poly, whatever I started with. So I start with ethene, my polymer is polyethene. Now, if I'm trying to draw propene, remember propene has 3 carbons, but I'm looking at the 2 carbons that have the double bond. I write it into a single bond and bond on the right and bond on the left, and I indicate that this is something that is repeated n times. Now I look at each carbon that had the double bond, it was bonded to what? One of them was bonded to 2 hydrogens, so I bonded to 2 hydrogens. The other one was bonded to a hydrogen and to a carbon that had 3 hydrogens. Can you see that? One butene, in the same way, one carbon was bonded to 2 hydrogens, the other carbon was bonded to a hydrogen and to a group that had 2 carbons and 5 hydrogens. Butene, the 2 carbons that had the double bond, each of them was bonded to 1 hydrogen and 1 carbon that had 3 hydrogens. So this is what I draw for the polymer. What's a fuel? A fuel is a flammable substance that burns in oxygen to release heat in an exothermic reaction. So burning of any fuel is exothermic. You should remember that we can have solid fossil fuel, liquid fossil fuel, gaseous fossil fuel. Remember that the only fuel that we don't burn in oxygen is uranium-235. So uranium-235 is used to produce energy in nuclear power stations. We can also use hydrogen gas as a fuel. It's actually used as a fuel in rockets. How do we get organic compounds? We get all organic compounds from petroleum. And what we do is fractional distillation, and that means the crude oil is heated and vaporized, then cooled and condensed in the fractionating column. Remember to know the order of these things, which one comes out first, and the use of each one. Remember that the one on top has less carbons, lower boiling point, more flammable. Okay? Then we take the things that come out from the fractionating column and we do cracking. Remember the conditions for cracking: 600, 700 degrees Celsius and aluminum oxide catalyst. And why are we doing cracking? Remember the importance of cracking. It produces shorter chains that are more useful, more in demand, higher prices, more profitable economically, and it also produces, one of its products is usually ethene, and this can be used to make polymers and ethanol. Metals, you should know that all metals conduct electricity because they have free moving delocalized electrons. Malleable and ductile, shiny, these are properties of all metals. You should be familiar with the fact that anything in group 1 is more reactive than group 2, more reactive than group 3, more reactive than transition. And this is what we have in the chemical reactivity series. Now, oxygen, all metals react with oxygen to give the oxide. And metal oxides are usually basic. We said some of them are amphoteric, but usually they're basic. So if I burn magnesium in oxygen, you should know the observation for this. The magnesium burns with a bright flame, and the magnesium oxide formed is a white solid. Now, one of the things that forms amphoteric oxides is aluminium, and that means that aluminium oxide can react with both acid and base. Sodium, if you put it in cold water, the sodium floats, darts, melts, vigorous fizzing. The bubbles of hydrogen gas may catch fire, and the solution formed is alkaline. It turns litmus paper to blue. This is because when a metal reacts with water, it forms the hydroxide plus hydrogen. Calcium also forms calcium hydroxide plus hydrogen, but in this case, this is group 2, so it sinks, strong fizzing, and the solution becomes milky. Magnesium will not react very quickly, at least with normal water. We have to react it with steam, and in that case it gives magnesium oxide and hydrogen. Magnesium burns with a white flame or a bright flame, and a white solid is formed. When zinc reacts, it also reacts with steam to give zinc oxide plus hydrogen. Reaction with acids, remember that any metal above hydrogen in the electrochemical series would react with acid. So copper is below hydrogen. You have to remember that copper is less reactive than hydrogen. So it does not react with acid and does not react with water. Displacement reactions, if I put a more reactive metal in the solution of a less reactive one. So zinc with copper sulfate. You should know that copper sulfate is a blue solution. Now what happens? The blue color of the solution changes to colorless. The zinc metal dissolves, or the zinc solid dissolves, and I get copper. That means I see a red precipitate or a red solid is formed. Rusting of iron, remember that in order to rust, iron needs both water and oxygen. What is formed is called hydrated iron 3 oxide. It is reddish brown and flaky in appearance. Now, to prevent rusting, the easiest way would be painting. And if he says, how does painting prevent rusting? You should realize that it provides a barrier that prevents iron from reacting with oxygen and water vapor in the air. This explanation goes also for oiling machines and for coating with plastic. In all these cases, they form a barrier that prevents reaction of the iron with oxygen and water vapor in the air. But galvanizing, when I cover it with zinc, now this prevents the iron from rusting because zinc is more reactive than iron, so it loses electrons and becomes oxidized instead of iron. Another method is sacrificial protection. This is where I put a bar of magnesium or a bar of zinc next to the iron. It's just touching it, it's not covering it. So just touching it, the magnesium or the zinc will lose electrons and become oxidized instead of the iron. Electroplating is covering a metal with another metal, so this also helps to prevent rusting. Air, you should know the composition of air, mostly nitrogen, oxygen, argon, and a small amount of carbon dioxide and water vapor. To obtain nitrogen and oxygen from air, we do fractional distillation of liquid air. What do we use oxygen for? We either use it in oxygen tents in hospitals and oxygen cylinders for divers, or we combine it with another gas which is called acetylene to form a flame that has a very high temperature, so it is used in cutting and welding metals. We have this kind of experiment where he says the copper was allowed to react with oxygen in the air, so the amount of the decrease in volume of air is used to determine the percent oxygen in the air. We prepare oxygen in the lab using hydrogen peroxide, and we add the manganese dioxide as a catalyst. If he says, how can I prove that it's a catalyst? I'll tell him at the end of the experiment, filter the solution, wash the residue with a few drops of distilled water, dry between filter paper, and reweigh. It should be the same mass as what we started with. Pollution, carbon monoxide is poisonous. Sulfur dioxide and oxides of nitrogen cause acid rain. So you should know that acid rain is caused by sulfur dioxide gas, which comes out from combustion of fossil fuels that contain sulfur impurities. This happens in factories. Or nitrogen oxide, which come out of car exhaust. So the sulfur dioxide, we said, sulfur burns in air with a blue flame to form sulfur dioxide. So if I burn coal that contains sulfur impurities, the sulfur in it forms sulfur dioxide, and the sulfur dioxide gas dissolves in the rainwater. Remember that when SO2 dissolves in water, it forms H2SO3, which is sulfurous acid. Sulfurous acid may then be oxidized in the air to form sulfuric acid, or the sulfur dioxide itself may be oxidized to sulfur trioxide, and this dissolves in rainwater to form sulfuric acid. Now, oxides of nitrogen, we said, come out of the car exhaust, or they are formed in car engines. This is because the high temperature of the engine causes the nitrogen and oxygen gas in the air around the engine to react. Now, in the end, the sulfur dioxide forms sulfuric acid, the oxides of nitrogen form nitric acid. This goes up and dissolves in the rainwater, and there are many bad effects of acid rain. If it falls on buildings, it dissolves the limestone in buildings and statues, causing them to crumble. If it falls on rivers, it makes the water in the rivers and lakes acidic, so it kills marine animals. It destroys leaves and roots and kills plants. And if he says what is the effect of acid rain on health, then you have to mention that it damages the respiratory system or it damages the lungs. We prepare carbon dioxide gas in the lab by adding acid to marble. Marble or limestone are forms of calcium carbonate. Now, how do we collect carbon dioxide gas? Remember that carbon dioxide gas is soluble in water, so I should not use that apparatus on top. I do not collect it over water. And I need to collect it by downward delivery because it is denser than air. We use carbon dioxide to make soft drinks because it dissolves in water to form acidic solution, so it gives it the sour taste. We use it in fire extinguishers because it is denser than air, so it covers the fire and prevents reaction with oxygen. How do we test for carbonates? We already said add dilute hydrochloric acid. Bubbles of carbon dioxide gas are formed that turn lime water milky. You should realize that calcium carbonate, different forms of calcium carbonate are limestone, marble, and chalk. So these are the common names of calcium carbonate. Calcium oxide, the common name is lime. And calcium hydroxide, the common name is slaked lime or lime water. So that is what we call lime water. If I'm starting with limestone, which is calcium carbonate, and I want to make slaked lime, calcium hydroxide, then I can heat it. It will form calcium oxide. Dissolve the calcium oxide in water, it forms slaked lime. And that's the end of the syllabus. I hope that this was useful and I hope it wasn't too long for you. Thank you for listening.